Uh, okay, good afternoon, everyone. It's time to start today's meeting. Today we have three presenters, Changben, Tomoki, and Priyanka. Who wants to go first? Thank you, Priyanka. Okay.
Okay, so I'm going to talk about this paper which the Tsuya-san actually put on Facebook, and it's quite relevant for what I'm doing. It's talking about first light simulations and the size evolution of these galaxies at redshift greater than 5. So the unusual thing is that we know this mass size relation of the galaxies, that more massive, the size is bigger, and that's the relation we knew from the previous study. However, when we see the JWST data, we see that there are some, like, there is a lot of scatter in this relation at higher redshifts. So the question here is why this scatter is there and why it does not follow the mass size relation at these higher redshifts. One of the complications why this has not been done before and why it is novel to this study is the dust attenuation. They use the simulation and also incorporate the dust attenuation in their simulation. So another thing about their simulation is that it's a very high resolution spectra of 10 proper parsec. And their goal is to basically study this size mass relation at higher uh, redshifts and connect it to the size, connect the size to the star formation rate, surface density, and the galaxy efficiency. So that's what they're going to talk about in their paper. I'm going to skip the simulation part because I am not really the right person to talk about it. You can read more about this in this paper. The only thing which I would like to point about in this simulation is that they basically generate the JWST images like these. And they generate these images for all 7 bands, and they incorporate dust. And the other thing is they incorporate the instrumental effect of the JWST. They also use the PSFs as mentioned in this paragraph. The other thing is that when they calculate the Cerseic index, they used something called non-parametric pixel-based method rather than using like a Cerseic profile fitting, because they say that at higher redshift, these galaxies can be quite irregular and clumpy. So using the standard methods which we use for low redshift galaxies may not be a good idea. So this is what an example of the simulated galaxies look like. This is without, the left panel is without any dust attenuation. This is the dust part, and then this is adding instrumental effects to the image. One thing you can notice is that the intrinsic size, if you see, of this galaxy is very small, but then when we include the dust, the dust, like the inferred size of the galaxies increases. That's what they are concluding in their first result, that the inclusion of dust severely attenuates the UV light of the central starburst in comparison with the spiral pattern. So therefore, the effective radius increases. However, they also mentioned that the instrumental effect broadens these features but does not affect the size determination. So that's what we see here in the images as well. They have put some more images. Example, this was a face on galaxies, and this was some edge on galaxies, some compact galaxy example. So coming to the second part of their paper, where they talk about the size and mass relation. So they say that this size mass relation is already known. But what they find is that there is a scatter. So if we see this image number 5, what they see is that this relation of size versus mass is there already present at higher redshifts as well from these papers. However, for every given mass, there is a lot of scatter in the radius. So you can see, I've just marked this one at say some 8 solar mass. You can see that there are some compact galaxies, but there are also some extended galaxies compared to the average line we have here. So what they're saying is that this scatter is not actually random, because the galaxies which have size greater than the average size is because they have higher star formation rate also, specific star formation rate as well. So you can see the blue points here. They are higher than the average, and you can see the specific star formation rate is also higher.
Mm.
And the one which are lower than this average value, so like these points, are actually lower because the star formation gas is more concentrated in the galaxy center, and that's why you see these compact galaxies as well. So this is what they find for the different redshift regime. The solid and dashed line is basically their fit, and the dashed is the extrapolated line for higher stellar masses. Yes, so that's what they have the results for. Yes, what they also say is, which sort of I don't agree with, is that their slope of this relation stays constant at even at higher edges. However, I don't think that this line actually fits the data. So this is very confusing for me. But they say that, especially like this part, they fit it for higher, like for masses greater than 9, and they fit this line. But for this, if you see that this is actually not fitting the data. And here we don't even have any data. So I don't know how they concluded for higher redshifts, but they do say that. Other thing is that the UV slope, and also they also study the optical slope. So they also study this relation for the size mass relation in the optical. And what they say is that when they do not include the dust in their analysis, then this spectral slope actually goes to negative. So this is in the table shown, table 2, that if they remove, if they do not add the dust, this is decreasing. So what they mean is that the size mass relation does not like evolve as we see for the low redshift, but actually it goes negative, and that means the massive galaxies are actually more compact. And this is happening due to wet compaction, which is basically the galaxy efficiency is very high. And it converts, following the stellar to halo mass ratio, it basically converts the gas to star very efficiently. And that's why when they see the star formation surface density increase with redshift, they say that it's actually driven by higher specific star formation rate, as well as a smaller physical size of the early galaxies. And that's why it results to a higher star formation rate. So then they plot this relation with redshift, and then you can see that this actually decreases with the redshift. And yeah, so from this point, one thing what I would like to talk is that you can see that since at higher redshift, the RE is very small. So for my analysis, when I'm looking for spiral galaxies, the first thing is the spiral galaxies at higher redshift are even rarer. And then also the size decreases. So this is a good point to take into account when I'm looking for giant spiral galaxies at higher redshifts. Yes, I think that's all what they have discussed in their paper. I think the major takeaway point is that at fixed mass, the galaxy size evolve very fast at redshift greater than 6, and it's basically because of high galaxy efficiency. I can stop, and if you have any questions.
Priyanka, I have a question.
Yes.
Thank you very much for reading this paper. So in figure 3, so I just wonder, this is about your research, but you have some candidates. Sorry, not 3. I think 4. I'm sorry, maybe 4. Size mass relations. Sorry, I'm sorry. Size mass relationship evolution.
This one.
This one. 5. Sorry. And it's, I think red orange is top left is redshift 5 to 6. So this
Yes.
is same as your redshift range, if I remember.
Yes, yes.
I wonder the candidates that you found
Mhm.
are outliers in this figure, or I just wonder.
Um, so, I mean, we initially started with outliers in this relation,
Mhm.
but in Cosmos field, there were some sources which do not have like the stellar mass estimates from the
Ah,
SEP.
okay.
So then we were missing a lot of. So actually, these were more like the rare cases were actually missing the stellar masses because the SED could not fit these rare cases.
Mm.
So then using this relation or outliers in this relation did not make much sense. So yeah, I mean, we started with it, but then we stopped.
I see, I see.
Yeah.
I understand. Okay, okay. So then if there's no mass measurement, then we
Hmm.
can overplot.
Yeah. Yeah.
Okay, okay. Thank you very much. Yeah, I think in general, if you can find the outliers in this figure, for example, well, I think that's
Yeah.
interesting. Kind of
Yeah.
say
Yeah. Yeah.
impossible
And
galaxies. It's
And
interesting.
interestingly, in their they actually mentioned this part in their simulation that um, so if you see this relation for the 5 to 6 redshift range,
Hmm.
it's not like there are not many outliers, if I would
Hmm.
say.
Hmm.
And they are actually mentioned that in their simulation they do not have a very rare cases.
Hmm.
So they don't have like the very compact galaxies or very large galaxies because
Oh.
of the box sizes and also because of the resolution effect. So these
Okay.
extremes are not there.
I see, I see.
Mm.
Hmm.
Yes.
Awesome. How do they, like for galaxies greater than redshift of 10, how do they say that this galaxy is spiral? Because,
Oh, so they don't say any spiral galaxies.
oh,
They went just for all the galaxies.
oh, so these are not
These are
spiral
not
galaxies.
spiral.
Okay.
I was just talking that based on this relation,
Mm.
this is for the entire galaxy setup,
Mm.
spirals, elliptical, and everything. You're saying, but you're saying that at even higher redshift, because the R decreases,
Mm.
and then also the spiral galaxies in general are expected to be rare at high redshift.
Mm.
So for me, finding a spiral galaxies at these redshift with the giant arm is rare. Big.
Yes.
So I too misunderstood a little bit here. So they obtain all the galaxies at that particular redshift and try to fit the Cersei profile, if I understand it
So this
correctly.
is basically their simulation analysis. This is entirely simulation, but the simulations are very similar to the JWST data, including all the galaxy types. They are not mentioning about any particular type of galaxies.
Okay.
Uh,
So if it is, I don't know, if the morphology is not resolved at higher redshift, how can they fit Cersei profile? How do they attempted to fit the Cersei profile?
yeah, this is what they say here that there is something called non-parametric pixel-based method, which they use for their simulated data to calculate the Cersei index rather than using the standard approaches for Cersei fitting because, as you said, they are
Okay.
irregular and clumped. Yeah.
Okay. Thank
Hmm.
you.
Mhm.
Okay, thank you, Priyanka. Any other comments or questions?
I have one more naive question. Sorry for the interruption. So, after this fitting process, do they
Hmm.
say how many of those simulated ones look like spirals in high
No,
C?
no.
Do they
I
have
was
a
looking.
number?
Yeah, I was looking for the same, but I did not find any like number of spirals or elliptical ratio.
Okay,
Yeah,
okay.
yeah. That would
So
have been very
sad.
nice for
Yeah,
my
yeah,
idea.
yeah. So sad.
Yeah.
It's okay. Thank you.
Okay.
So also in the figure 4, the mass size relation, it seems to have a bend over towards the low mass range, right?
Yes.
But when the high redshift part,
There is no bend of.
Yes.
Yes, that I agree. That at lower stellar masses, they have this intrinsic static even within like the mass range as well. But they do not explain that part. And that's why I was like, they only fit the relation for stellar masses greater than 9. They do not talk about this. But what I could understand is that it is again the dynamic play between the star formation, as well as like how the again it's connected to the star formation rate only. That if it is like if you see in this line, this plot, the star formation is very less.
Yes, yes.
And that's why the mass is high for the same radius. And if you see the star formation rate is higher here, and that's why it's less stellar mass and at the same radius. Basically, these three parameters play together. That's what I understand.
It's also possible that at higher redshift, so the below this plot, at higher redshift, there's not many 10 to the 10. Yes, yes.
That could be possible. Yes.
Thank you.
Okay, thank you. So, who wants to go next?
So, okay, let me share my screen. Okay, so originally I don't know which paper I want to present because there are many interesting papers, and some of them are having like very famous author list. And eventually I pick out this paper. I couldn't see this cursor. Oh. Okay. So you can see the author list: famous Simon White and Gao. And the final decision I made for this paper is because they signed my papers. So, okay. So this paper is the capture of halo material by orbiting subhalo. It was originally proposed by Lee's paper, I think it's 2005 by Nebula. Say they have these like, for example, this figure, you have a galaxy, host galaxy, and a dark halo that falling into this host galaxy, and potentially they can capture the field star of this host galaxy, not the star in the like disk or bulge. The field star, that means, is the loosely bound stellar halo. So when the overdensity of this subhalo that goes into this C of the uniformly not uniform, the star particle that can capture these star particle, and then potentially looks like it has stars, but in fact these subhalo are too less massive, so they couldn't have formed star in the beginning, but they captured by this process and potentially make them visible in the observation. And this was a very surprising thought. And then I think they have done many tests and claim that if for a 10 to the 9 host galaxy and for 10 to the 7, no. So I think it's, no, I forget the host galaxy is Milky Way mass or something like that. But eventually they capture the star, like the red point, is possibly around 10 to the 7 solar mass. So you would think that maybe it is possible in a observable range. But in here, this paper, they do a more realistic unbody simulation to check if it is possible to observe So maybe I can jump to figure 1. Figure 1 is probably also showing a similar thing. So that have like redshift 1.1. That is the time when the subhalo first info. And the red dot is the capture star later. It will capture at redshift 0.1. And forget the red dot at the middle panel. It is just saying that the stars, the capture star, are easily lost by this orbiting motion. And redshift 0 is the end of the simulation. And the red dot is the capture star at the potentially capture star at redshift 0.1. So it is saying that the red point here is the position of red point at the right panel. So unfortunately, there's not many red point that can retain inside the tidal radius of this subhalo. So figure 2 is just a simple single case. So I think it's easier to watch figure 4. So they stake all these subhalo in their simulation, and the info redshift for this figure is 1, and the density is divided by the background density, and the radius is divided by the tidal radius. So the retain, so the red line retain is the originally dark matter particle, plus potentially they didn't mention clearly, but I think this also plus the permanent capture of the dark, star particle. And the cyan line is the newly associated. So this is the capture star after for the next snapshot, they will be inside the tidal radius. So the short story. Oh, I also have to mention the number of info particle is around 10 to the 10 to 10 to the 10 to the 2 to 10 to the 3, and no matter how you increases the original dark matter halo particle number, namely the mass of the dark matter subhalo, or increase the number of orbit it completes its orbit, the cyan line is almost around the unit of the background density. So that means no matter how you increase the size, the mass of the subhalo, or how many orbit it finish for this subhalo, the newly captured by this subhalo is still the level of the background density. And figure 5 is showing for if they have longer time integrated. So the redshift info is from 1 to 2, so you have longer time for it to capture. The newly associated is still at the background density. So that means things go in to the tidal radius of this subhalo is as quick as it go out. And oh no, not this paper. And the final figure they want to show is figure 7. So they put the velocity space, and the red circle is the escape velocity of this subhalo. So you can calculate the potential of this subhalo and then get the velocity, escape velocity. So you can have a region that how many particles inside this region can permanently captured by this subhalo. And the cyan dot is newly associated. So basically, not many particles can be permanently captured by this subhalo. the velocity is too high. So I guess that's it. The paper just trying to say these the previous assumption of this capture of field star is not efficient enough for subhalo, like the no star forming purely dark subhalo to become visible if they fall into a galaxy and capture its stellar halo. Because if you have only have the star captured by this subhalo is exactly the same as the background density, then you have no chance to see this subhalo in a observation. And even you do the like detailed velocity inspection, they are not able to show in these capture radius. So I guess that's it. They signed my paper here.
Cool. I have one naive question.
Oh,
When they assume this starless halo at the beginning,
Hmm.
so how many of them are expected? Say this kind of halo without stars are really common in this galaxy formation.
Yes. So the halo halo mass function is suddenly forget the name. So halo mass function in lambda CDM model keeps going up at the low mass range. So up to some range, for example, like 10 to the 8 halo mass, the mass of these halo are not massive enough to cool the hydrogen gas. So up to some low mass range, like most of the dark matter halo will be starless.
Oh, okay. But they are not directly visible because there's no stars.
Yes.
Okay, that's interesting.
Thank you, Changman. Any other questions or comments to Changman? If no, we can move on to Tomoki. Sorry.
Okay, vitamin.
Changman, please.
Can you see my screen?
Yeah.
Okay. Today I'd like to introduce this paper. This paper is kind of a theoretical study regarding FRB dispersion measures. And they calculate the dispersion measure from the local environment. They use numerical simulation and calculate the dispersion measure comes from the local environment of FRBs. And let me show very naive structure of FRB and surroundings. This is a schematic picture of FRB, so neutron star and wind nebula and supernova remnants. And because neutron star or magnetars are formed after a supernova explosion, they are inside this kind of structured material around neutron stars. And FRB is emitted from here and propagates these surroundings. And at last, we observe FRBs. And there is detailed structure. This structure is very detailed, something like shown here. I don't explain the details of the structure, but important point is there is almost very naively, there is two components. One is circumstellar media. Here they show ISM, but truly here should be circumstellar materials. And the other one is pulsar wind emitted from here, and they collide and form this kind of very, how to say, difficult structures. Sorry, there's three components. One is circumstellar medium, and the other is supernova ejector, and third is pulsar wind nebula. So sorry, there's three components: CSM, supernova ejector, and pulsar wind. And in this study, they numerically simulate this kind of structures and evaluate dispersion coming from this component. They are, so okay, let's go details. From observation, we can calculate, so we can measure the dispersion measure of FRBs. And dispersion measure is decomposed something like this. And what they are focused on is source star of dispersion measures. And they don't, maybe they don't show very, how to say, naive pictures, but what they calculate is just numerically demonstrate this kind of structure. And maybe important point is they solve hydrodynamics and, I say, non-equilibrium, sorry, it's this one, non-equilibrium ionization of this kind of structured material. Because ionized electron can, dispersion measure comes from dispersion measure comes from ionized electron. So solving this non-equilibrium process is important to check the dispersion measures. This is one of important points, and the other is they did numerical simulation, not analytical one. And they explain very detailed, but very naively they calculate four models: single star, binary, and different zero-age mass of different terms of progenitor stars. And let's go result. Maybe important figure is here. Oh, sorry. This, okay. This figure shows the time evolution of dispersion measures. Yeah, okay. The time evolution of dispersion measure and mean number density of electrons and maybe size of the expanding shells. And they calculate this kind of trend, and TM can decrease along time, maybe in the time scale of about 100 years or so. Because they did simulation, they can estimate which component contribute dispersion measure significantly. And this figure shows that kind of structures. This blue line shows full dispersion measure, and this green line shows unshocked ejector. This is supernova eject. And this red shows shocked supernova ejector. And this dotted line is circumstellar matters around supernova ejector. And important point is first, unshocked ejector contributes its dispersion measure significantly, and later it becomes flat because unshocked circumstellar material becomes significant to dispersion measures. And they also evaluate the slope of this curve, which is about t minus 2. And this slope is independent of initial conditions. And there was some observation for the time evolution of dispersion measure and rotation measures. In order to explain these observed ones, they tune models for these FRBs. And no, they only know the time evolution of dispersion measure and rotation measure. And they just fit age and parameters to tune to match the calculation and observations. From this information, we can estimate the age of source. This is done by their calculations.
Okay.
And this is time evolution of rotation measure. And
Tomoki-san, sorry.
Right.
Regarding that point, so this time is time since supernova explosion?
yes.
Okay. Thank you.
Yeah. Almost like that.
Also like this. Okay. Thank you.
This is the fitting of rotation measure evolution of this FRB. And sorry, they don't. There should be dispersion measure evolution, but sorry, I missed the comparison between observations and simulation, but they calculate the time evolution of dm dot, something like this. And using information of dispersion measure time evolution and rotation measure time evolution here, they estimate the age of these sources. Maybe supernova explosion should occur within 100 years for these sources. Maybe result is not so special, but what the important point is they confirm this result with numerical simulations. I think this is important point of this paper.
I think this kind of calculation is easily done analytically.
Yes.
And the point is maybe checking both single and the binary system. And could you explain which projector system predict higher or lower DM? This cannot be treated analytically.
From here?
Yes.
Can show this result? Okay. This dash, please compare this dash to, for example, for low mass progenitor, 11 solar mass case, the lines both blue and orange shows difference between single and binary. For this case, the time evolution of dispersion measure is very different. Initial value of, let's say, dispersion measure is very different, but let's say. This is because they also track the stellar evolution using NESA code. And that maybe the difference between wind mass, sorry. The difference in ejecta mass changes.
So final remnant is always neutron star, but
yes.
At the time of explosion, the ejected mass, remnant mass changes. So that's why. I mean, the ejected mass changes.
Because of binary interaction or single evolution.
For massive system, there is no such significant difference.
Yes.
Okay.
I'm not sure why this occurs.
I would say this is the only new part.
No. Not this point, but they solve. They check the ionization effect, ionization fraction. This is important point.
I think ionization is also treated numerically in the former previous work using cloudy. So,
but in that case, this analytic analytic modeling and numerical value of ionization. But in this case, they solve explosion and ionization effect consistently in single simulation.
I see.
I think this is the important point for this calculation.
Thank you.
Thank you very much for checking. Thank you for the comments. Yeah, I think that's all from this paper. And they also discussed the free absorption of FRBs, but I skip this part. Okay, thank you very much.
Thank you, Tomoki. I think Vignesh have question.
Hi, Tomoki-san. I have two questions, but could you go to the figure 5 first? The comparison between unshocked CSM and this guy. Yeah.
Yeah.
So my first question is, how do they resolve or differentiate whether this DM contribution is coming from unshocked CSM or this contribution is coming from pulsar wind? Because if I remember in the dispersion measure equation that you showed, there are only two components. One is from host galaxy, one is from source. But here they are comparing different different steps that you showed in the first figure, the model figure.
Okay.
If I remember, how do they differentiate that?
Maybe I skipped that part. They did one-dimensional numerical simulation for this kind of structures, all of these structures.
Okay.
So from this calculation, so using this, how to say, something like this, using this result of numerical calculation, we can estimate.
Okay, so they are taking the profile of all the components, right?
Yes, yes, yes.
Okay. So that answers my first question. So the second question is in the same figure 5.
Okay.
Yeah. So at the time scale of 100 years, I mean like very far end, on the top left panel, yes, there is an excess of DM host. I mean, sorry, there is an excess of DM blue colored solid line, which is not fitted by the unshocked ejector or unshocked CSM. So do you know what is the reason of the?
You mean here?
Yes.
This is because this blue line is a summation of all of them.
Oh.
So this is maybe factor 2 also, I think.
Oh, okay.
Is it clear?
I think yes. I didn't see there is another dotted line. Okay, now it makes sense.
Yeah.
The flat one.
Yeah.
I was thinking, I was only checking 3 lines: the red dotted
Okay.
and the green dotted and the blue solid. Okay.
Yeah, it's CSM component.
Okay. Makes sense.
Dominant later.
Makes sense. Thank you.
Okay.
Tomoki-san, I have a very small question.
Okay.
In figure 7, this DM change rate is interesting to me. Then in the legend, they say this FRB 2019 and 2012.
Yes.
But in figure, I don't see these markers. Where are they? The black dotted and the black dashed line. Which is this?
I'm not sure, sorry.
Vertical
line, yeah, looks this. Maybe
but then vertical line means, do they know that time since the explosion?
Sorry, I'm not sure about that point.
When I read the caption, the caption also, I don't really understand this caption. So I wonder, where is the observed data in this diagram?
I think they should have observed data.
That one should be, they have measurement, right?
Yes.
Then I thought kind of horizontal line or something like that, but I don't really see. Okay.
I don't know why this is vertical lines.
Okay. Then.
Sorry, I thought similar to this process was done for dispersion measure, but might be different.
Oh,
This kind of
okay.
fitting.
Mm.
I'm not sure. Sorry.
Thank you, thank you. Actually, this reminds me that there might be a possibility of missing repeaters. Say, in this case, they are saying that DM changes across time, right?
Yes.
And then this DDMDT could be higher if progenitor is very young. Then even within 1 year, it could change. It could be kind of significant change. So therefore, when Chime people identify repeaters, they use this DM measurement across different time. Say if their position is overlapping on sky, and then DM also is the same, then they classify this as repeaters.
Yes.
But if DM changes as a function of time, then even if it is truly repeaters overlapping same position, two events overlapping, but if DM changes, then maybe this is missed from current definition of repeaters. Therefore, I wonder. Actually, we checked this point using Chime catalog 1 before. Then finding no significant case. But then now we have Chime 2, so I was wondering maybe this is interesting to come back again. If we can, then if we can find a candidate, that's maybe interesting. Also, we can cross-check with past supernova events. So that's maybe possible.
Very consistent story.
If we can find it, therefore, I think it's good to quickly check data, I think. That's interesting.
Thank you very much.
Okay, Vignesh also have, I think, another question. Vignesh?
Tomoki-san, I don't know whether this is possible or but I was wondering, since now they are having a resolved like they resolved the dispersion measure and truly figured out the source dispersion measure and the ionization fraction, I was wondering, is it possible to figure out what could be the scattering due to that plasma surrounding the source?
I think it's possible.
Because if we can do that, then we can figure out how much this quantity affects the total scattering profile of the entire FRB.
Yeah, I think it's possible. And in introduction, they mention about scattering, but I don't know whether.
Because as of now, scattering is only taken as the propagation effect. But if we can find significant scattering profile in the source medium itself, intrinsic to the FRB, I think that could be something interesting to check.
It might be, but I'm not sure whether the scattering made by source or host. We should check that one. Some paper assume it's host, I think, but not sure. Sorry. Yeah. Thank you very much, Vignesh. I think it's one interesting application. Okay, thank you very much.
Okay, thank you, Tomoki. Is there any other questions or comments to Tomoki? If no, we can decide on next week presenters. For next week, we have three, yes. Okay. Okay, now we have 4 presenters, I think.
Then I'm fine. Go with Tetsuya and Chakri.
Okay, thank you.
Okay.
Thank you very much. If there is no comments, we can close the meeting. Thank you for attending.
Thank you.
Thank you.
Thank
you.
See you.
Goodbye.
Goodbye.